lecture 9, I like to give some expressions of different type of average speeds. First of all, I come to the most probable speed, then average speed, and then RMS speed. And we shall also compare the values of these three and the cause for the difference of these three types of speeds. So, I have already given you the Maxwell's distribution law. Which is dNc by n. It is the fraction of the molecules having the speed c within dc, and this is equal to the 4 pi and m by 2 pi kt to the power 3 by 2 e to the power minus mc square by twice kt and c square dc. That also we can write this FCDC, where FC is the distribution, or you can say the speed distribution function, and which is equal to 4 pi m by 2 pi kt to the power 3 by 2 to the power minus mc square and mc square by 2 kt into c square, where dnc is the fraction of the molecules having the speed c within the short range infinitesimal range dc, where fc is the fraction of the molecules having the speed c, virtually speed c. And also if we plot this here c speed and here fc starting from this origin, then this graph already I have discussed as this one is like this. This graph starts from 0, increasing, attains maximum value and decreasing exponentially and becomes asymptotic with this axis C. And also we have defined this one is the maximum fraction of the molecules, and this maximum fraction of the molecules have this speed c, and it is called the CMP, most probable speed. And the value of this most probable speed you can calculate. You can find the expressions of this most probable speed by using the differential calculus conditions. These are the two minimum, and this is the extreme. So condition for the extrema in differential calculus is that dfc by dc equal to 0. So let us first differentiate this fc with respect to c, and then we justify which speed will be the most probable speed. So this fc we can write this one, we are differentiating FC with respect to C, and this term is constant. So this constant terms we can write this A dash. So this is A dash, and e to the power minus mc square by twice kt, and here this is c square, but dfc by dc, when differentiating with respect to c, we get a dash, and here e to the power minus mc square, one term we are keeping constant, and c square differentiation into twice c, and plus c square now constant, and it is e to the power minus mc square by twice kt, and here this exponential term, this term again differentiating with respect to c, and so this will give you the twice mc by twice kt, and bracket close. So this one actually a dash constant, and you can take the common twice c and e to the power minus mc square by twice kt, and so in this case here it is minus, so here 1 and minus 2c constant, so mc square by twice kt equal to 0 if we put this condition for the maximum and minimum here. So three conditions, three options. Three options we may come. One option is c equal to 0. C equal to 0. Then also this dfc by dc equal to 0. C equal to 0. So this is the condition for c equal to 0. Means this is the condition. This is the minimal conditions. Minimal condition of FC versus C curve. Against 2, this term may also be equal to 0. So e to the power minus mc square by twice kt equal to 0, or c equal to infinity. So this is also the minimal condition of FC versus C curve. Then third one we can write 1 minus mc square by twice kt equal to 0. So this is the minimal point, then this third option will give you the maximal point of this curve, and that C is the ms the most probable speed. So we can write or 1 equal to mc mp square by twice kt, or you have the expression cmp equal to root over of twice kt by 8, or you can write this is twice RT divided by K. When A is replaced by the molar gas constant, molecular mass is replaced by this molar mass of this gas. So we have got this expression. we have got this expression CMP equal to root over of twice KT by N. This is one expression. And we can also give you one problem to calculate this CMP for this oxygen gas at 300 Kelvin. So here CMP, you can write this root over of twice RT divided by capital N. Now if we calculate CMP of oxygen gas at 300 Kelvin, then then CMP equal to root over of twice into 8.31 joule mole inverse Kelvin inverse and into temperature 300 Kelvin and divided by M for the oxygen is equal to 32 into 10 to the power minus 3 kg mole inverse. So mole inverse cancel, Kelvin cancel, and joule per kg root over joule you can split up this kg meter square and second inverse 2 and divide by kg. So kg cancel, this will give you the meter per second. So this value, whenever you do this calculation, the value will come up. The value will be 394.7 meter per second. So for oxygen gas at 300 Kelvin MCP equal to 394.7 meter per second. Now we like to calculate. We rather like to show that this CMP, that FC, the fraction of the molecules having the most probable speed will decrease with this temperature. This is also very important question set in Calcutta University. I will show it. So this FCMP equal to 4 pi and 4 pi into m by 2 pi kt to the power 3 by 2 and e to the power minus here m, and instead of c we can write CMP square divided by twice kt, and here also instead of c we can write CMP square. So we know that the CMP equal to twice kt by m, so this is equal to 4 pi m by 2 pi kt to the power 3 by 2 and e to the power minus 1. CMP square equal to 2 kt by m. So e to the power minus 1, and here also twice kt by m. If we keep the variations of this CMP with the temperature, keeping all other factors constant, then we have 4 4 and pi means pi to the power half m to the power half kt to the power half. So it becomes 2 and 2. So it becomes m by 2 pi kt to the power half and e to the power minus 1. M, here m to the power 3 by 2, so 1 m is there, and kt, 1 kt is there, and here 2 included, so 1 2 is there, so this one. Or we can write this 4 into capital M divided by twice pi RT to the power half e to the power minus 1. So it is saying that this FCMP is proportional to 1 by T. 1 by T, 1 by root over T. 1 by root over T. Keeping M and for a particular gas, this FCMP is decreasing with the rising temperature. This could be solved. And this problem has been given. This problem has been given. So we can write this HCMP, and this is actually 4 into m divided by twice pi RT to the power half e to the power minus 1. Now I show the problem. Now I show the problem which has been set in Calcutta University for an problem for an ideal gas. Ideal gas obeying Maxwellian distribution. Distribution of molecular speed. Molecular speeds in 3D motion, 3 dimension, find the maximum value of 1 by n dn divided by dc for a gas of molar mass 4.0 gram mole inverse kept at 127 degree centigrade. So this is the problem set in Calcutta University in 2012, and mark is 3. Mark is given 3 for this problem. So this one we can easily calculate this value. So we can put here the values. If CMP maximum value of this one is equal to 1 by n in our terms. In this university, this instead of n, they have given this capital N. So this is the 1 by n and dn divided by dc. So if we insert the values here, then we get this is equal to 4, and instead of n for the 4.0 gram mole inverse and divided by 2 into 3.14 into R 8.31 here CGS unit R into 10 to the power 7 R mole inverse Kelvin inverse and T 127 means 400 Kelvin to the power half and to the power minus 1. So if we do the calculation to this problem, then this will come up Kelvin inverse cancelled, mole inverse cancelled, and similarly instead of R you can write this gram centimeter square second inverse 2. So this numerical value will come up 6.44 into 10 to the power minus 6, and this gram will cancel. It is in root over, so it will be centimeter per second and to the power minus 1 to the power minus 1. So this is actually the problem solution to this problem which has been set in Calcutta University in 2012, and the mark at the time giving 3. Now I come up to this expressions of this average speed. Expressions of this average speed is C bar. From this distribution you can get this average speed, and I have already told you that from the distribution of a property, the best benefit is that we can get this average value of that property. So C bar, if we write this C bar, which is the average speed of the molecules, then it will be integration 0 to infinity, and here C and dnc by n. Fraction, it is the probability of a molecule to have this value C, and C is ranging from 0 to infinity. So if we put here, then 4 pi and m by 2 pi kt to the power 3 by 2 will go outside of the integration, and here c square and c cube 0 to infinity, and e to the power minus mc square by twice kt and into dc. Into dc, c square and c giving you c cube. So this integration you can solve very easily by the use of gamma function. Say b equal to, let b equal to m by 2 kt. Then this c bar equal to 4 pi m by 2 pi kT to the power 3 by 2, and this value I have also given you that integration 0 to infinity x to the power n e to the power minus b x square dx, this value is equal to gamma n plus 1 by 2 and 2 b to the power n plus 1 by 2. Here n equal to 3. Here n equal to 3. So this will give you 3 plus 1 by 2 means gamma 2, and here 2b square. So if we insert this value of b, then 4 pi into n by twice pi kT to the power 3 by 2, and gamma 2 1, so 2, and b square means it is half, and b square means 4k square b square divided by n square. So if it is better 2 you can cancel. It is better to solve if you keep all the terms under the square root. So this will under the square root. If you write all this one, then it will be 16 pi square, and this one is m cube, and here it is 8 pi cube, and here it is k cube, t cube, into here 4 and k to the power 4 and t to the power 4 divided by m to the power 4, and this will give you this 2. So it will be root over of 8 kT k cube, k to the power 4 cancels, only 1k is there, 1k is there, and t cube only t is there, here only n, so 8 kT by pi, here pi n. So we have got this expression of average speed. So this average speed c bar is equal to root over of 8 kT by pi m, or you can write 8 RT by pi capital M. So this one, you can see this one is greater than this one. If you calculate, average speed of oxygen molecules at 300 Kelvin at identical temperature for the same gas. We compare what will be the what value, whether CMP or C bar greater. Then in this case, this C bar is equal to, you can write 8 RT by pi and capital A. So here 8 into, instead of R, you can write 8.31 joule mole inverse Kelvin inverse into temperature 300 Kelvin, and divided by, this is 32 into 10 to the power minus 3 kg mole inverse. if we do the calculations and considering if we do the calculations, then it will be 445.5. It will give you the 445.5 meter per second. So for the same gas and identical temperature, this value for oxygen gas at 300 Kelvin, C bar is equal to 445.5 meter per second. So obviously it is seen that the average speed is greater than most probable speed. Why this value is greater than this one? Actually, average value will be the balancing point. Average value is the balancing point of this curve. If this curve would be, here C and here FC and here it is 0 and if this curve would be symmetrical, if the curve would be symmetrical, then in this case this CMP equal to C bar, as this will be the fulcrum and balancing point. So this CMP is less than C bar. So this is this you can write the same curve, the C bar. See, this curve is inclined. This curve is not symmetrical. This curve is Maxwell curve. Maxwellian curve is not symmetrical, is inclined to the left hand side, to the lower side of this speed, and this is why the most probable speed is less than the average speed of the molecules. Now I am coming to the RMS speed, expression of RMS speed of the molecules. RMS speed, you can write in short the CRMS speed of the molecules. So from this distribution, again we can calculate this average, calculate this RMS speed, and C square bar. Let us first calculate this average mean square speed. Mean square speed again 0 to infinity, and here C square dNc by A, and this will give you this instead of dNc by N, we can write 4 pi and m by 2 pi kt and to the power 3 by 2 and c square c to the power integration 0 to infinity to the power minus mc square by twice kt into c to the power 4 into dc. We have already calculated this value earlier while we have derived this Maxwell distribution law, and this can again you can find the integration very easily by the use of this gamma function, and so this will give you 3 kt by A. So c square bar root over, which we call the C RMS speed, and this will give you this 3 kt by A, or you can write root over 3 RT by A. So we can list list up here. We can list up here this CRMS is equal to root over of 3 kT by m, and for oxygen gas or oxygen gas at 300 Kelvin, CRMS, if we do calculate, then CRMS equal to root over of 3 RT by capital M. If we put all the values, root over of 3 into 8.31 joule mole inverse Kelvin inverse into 300 Kelvin, and divide by instead of molar mass in SI unit 10 power minus 3 kg mole inverse. Mole inverse cancel. This one also cancel, and this give you. If we split up the joule as I have did earlier, joule equal to kg meter square second inverse 2, then it will give you the value for this oxygen. For the oxygen, 483 483.4 meter per second. So this value is 483.4 meter per second. So obviously from this numerical value of this oxygen at for the same gas at the same temperature, if we compare the magnitude of these three types of speeds, then this one is the highest one, this one next to this one, and this next. This is the lowest. That it means that CMP is less than C bar, less than C RMS. So C RMS value. So this will give you this C RMS. So in this graph we can plot these three types of speeds, and lowest one is this CMP, then next to CMP more higher C bar, and then it is the highest one. So you can also get this numerical value. This one CMP, this one is the C bar, and this is the C RMS. You can get this proportionality also. Say CMP and CMP is to C bar is to C RMS is equal to root over of twice KT by M is to 8 KT by M by M, and is to root over of 3 KT by M. So if you take this common KT by M, then it is root over of 2 is to root over of 8 by 5 and is to root over of 3. Or if it is taken 1, then 1 is to, it will be root over of 8 4 by 5 and is to root over 3 by 2. If we do calculations, then it will be 1 is to 1.13 is to 1.22. So this is the ratio. If you know this one speed, then other average speed you can calculate from this ratio. Now I am coming to coming a new idea, standard deviation. Standard deviation is the root mean square deviation, and the standard deviation measures the spread or the breadth of this distribution. Greater the spread of these speeds of the molecules in a gas assembly, more will be the standard deviation. And standard deviation very important term in different chapters, especially in the analytical chemistry. Standard deviation symbolized as S, and it is given as del square bar and root bar. And deviation del is equal to deviation means deviation of the speed from their mean value. So this is the C minus C bar. So C is the speed of the molecules and C bar is the average or mean speed. How much the deviation sigma is coming up. So let us I have already told at a given temperature the gas maintains the steady state conditions, means definite fraction of the molecules will have a definite speed, and this is called this steady state conditions of this gas at a given temperature. So let us say N1 molecules have speeds C1. N2 molecules have speeds C2. N3 molecules have speed and C3 and so on. This is the distribution of the speed among the molecules at a given temperature under the steady state conditions. So this is del square. So del square bar, it is the mean square deviation. This is equal to N1 into del 1, means N1 molecules are having the deviation del 1 plus N2 molecules having the deviation del 2 plus N3 molecules having the deviation del 3 plus dot and divided by N. N is the total number of molecules, N1 plus N2 plus N3 plus. So instead of writing this N1, instead of writing this del 1, it will be C1 minus C bar and it is squared. We are considering the mean square deviation. So it will be squared up. So square plus N2 into C2 minus C bar square plus N3 into C3 minus C bar square plus and divided by N, total number of molecules. So if you split up the square terms, then N1, and it is the C1 square minus twice C1 C bar plus C bar square plus N2 again C2 square minus twice C2 C bar plus C bar square bracket close plus N3 into C3 square minus twice C3 bar plus C bar square and bracket close plus dot dot, and this will again be divided by n. Divided by n. So now we can also multiply this n1 c1 square, n1 c1 square, and minus twice c bar common, and n1 c1 square, then right here plus n2 c2 square plus here n3 c3 square divided by n, and minus 2c bar common, and here also this n1 c1 plus n2 c2 plus here n3 c3 and plus dot dot divided by n, and plus here all are c bar square, so c bar square will get common, and here n1 plus n2 plus n3 plus dot dot and divided by n. So this one will give you the c square bar, mean square speed, and this one minus 2 here c bar, and this is also c bar, minus 2 c bar square. This term within the bracket, the average speed, and plus this one c bar square, and this total n1 plus n2 plus n3 equal to n, and here n will cancel, so only this one left. So if we simplify this one, then c square bar and minus c bar square. It is the mean square speed, and it is the square of mean speed. The difference between the two is the mean square deviation. So we can write here del square bar, this is equal to standard deviation, and this will give you the root over of c square bar minus c bar square. It is the mean square speed and is the square of mean speed. Actually, this one square term, so square term is always positive, and so this standard deviation is always positive, and this shows that the c square bar root over or c square bar is greater than c bar square. Or you can write the c square bar root over, which is RMS speed. RMS speed is greater than this average speed. This way you can also show the RMS speed is greater than the average speed. If you try to calculate the value of standard deviation, this is the root over. So standard deviation is equal to if you insert the values of mean squared speed and the square of this mean speed, it is the 3 kt, 3 kt by n minus, it is 8 kt by 5n. So you can write here root over kt by n common, and here 3 minus 8 by 5. And this value will come up. This value will give you this value will give you 0.67 and root over of kt by n. Or you can write 0.67 and root over of RT by capital M. In this way, you can write 1. So from this significance of the standard deviation, is that greater the value of the standard deviation, the more spread or more breadth of this distribution curve. If the value of S is smaller, then breadth or the spread of the velocities or speeds are also very less. This is the significance. You can find an immense applications in analytical chemistry whenever you are doing this analytical determination, quantitative determination of the ores in of a metal in ores. Several experiments you are doing and also getting this standard deviation. It is precision. It is in the chapter of precision and errors. One question I can show you in Calcutta University. Calculate the difference. Calculate the difference between RMS speed and average speed for an ideal gas. Maxwell distribution, again I can recall the Maxwell distribution is valid only for the ideal gas where there is no intermolecular interactions. So ideal gas exhibiting Maxwellian distribution of molecular speed. Given the molar mass is 2.0 gram mole inverse and density is 0.089 gram liter inverse and pressure and pressure is 1.0 atmosphere, and this is the problem. And if you like to find a solution, if you like to find a solution, difference between the RMS speed and average speed. So this S equal, you may calculate this value of S. S equal to 0.67 into root over of KT by AM, or you can write this RT by capital A. So for this gas, for this ideal gas, PV equal to nRT, or you can write this P equal to PV equal to G by M RT, or P equal to G by V into RT by M. So instead of RT by M, you can, this is density. This is density into RT by M. So instead of RT by M, you can write P by D. Instead of writing this RT by M, you can write P by D. So this will give you 0.67 into P by D. So pressure is given, density is also given. So you can calculate this value. You can calculate this value. Putting this one, you can calculate the C RMS minus C bar. You can write this equal to 14,516 centimeter per second. This will give you the difference. Now, next the task is to actually we have shown that the average speed or average value of this property you can calculate, you can find an expression from the distribution curve. Not only these speeds, but any property related to the speed, you can also get it average from this speed distribution. Say one thing, the expression of average time required to travel unit distance, and it could be written as a T bar. Average time required to travel this unit distance. So T equal to 1 by C. So this t bar equal to integration 0 to infinity here t and dnc by dnc by n equal to 0 to infinity. Instead of t you can write 1 by c, and it is the instead of dnc you can write 4 pi m by 2 pi kt, and to the power t by 2 e to the power minus mc squared into c squared dc. So 1c and 1c will cancel. So you can get a 4 pi m by 2 pi kt to the power t by 2 e to the power minus mc squared 0 to infinity, and mc square by twice kt and c square dc, and here twice kt and c dc. You can also calculate the standard deviation, standard integration by means of this gamma function, and total expressions you will get this t bar equal to root over of twice m by pi kt, or you can write this t bar, the average time required for the molecules to travel unit distance is equal to root over of twice capital M divided by pi r2. And from this expression you can calculate any problem if it requires. So this is all about the different type of speeds and different problems, allied problems. And in my next class I like to convert this speed distribution formula, Maxwell's speed distribution formula, into the kinetic energy distribution formula. Kinetic energy could also be distributed and that could be obtained from this speed distribution formula or momentum distribution formula. Anything you can get this distribution which is directly related with this speed of these molecules. So this is all about today's lecture. Thank you all who are watching my video.